Thank you very much. Very kind introduction, Andrea. These are the laboratory of the University of Siena, and most of some of the photograph that I showed today was done with our company, which is a company in Siena, esteemed by former students, and we have some stellar collaboration. And we put the photo of the marine outburst of the barge. Part of the presentation. Appropriate. For the board. What they use this. Oh, okay. Do this. Remove it, it doesn't work. I think it's really like it doesn't work either. It doesn't work. Oh, look, it's weird. I am not. Right? Okay. So, concerning with Metasurface, there are several generations of Metasurface that we faced in this last year. The first generation of the Metasurface was uniform, next space modulated, space and time modulated. And this is the trend today toward going into configurability and time binding with several platforms. One of the things that is interesting is that if you look at the key word Metasurface and metamaterial into the old journals, I mean physics, photonics, electromagnetics, radio frequency in general, you will see that this year the word metamaterial and the word Metasurface are mentioned at the same time, at the same number. So this happened just this year. When you go into antenna-set propagation, there is a journal for antenna-set propagation community. This happened in 2016. So, which is the reason of it? The reason is that Metasurface are easy to be fabricated for antennas with respect to metamaterial. Because you can use directly a printed circuit printed board, like this. And we concentrated today with this particular type of antenna, which is formed by redeveloping the same technology as a special technology, very old technology. But the concept is different. There are very, very small elements that have a modulation. The modulation gets a sort of memory of the wave when it interacts. And this is something that yesterday we discussed very well. And on one end, you get this modulation excited with surface wave, and as whether the surface wave match the periodicity of the modulation, you have a bright thread that gets the broadside beam. Then you can not only have the broadside beam, you can modulate the different waves, elliptical line, you get a tilted beam, or you can do much more. If you can modulate the Metasurface different way in each point, you can also tailor the alpha of the leakage. So you can also make a very high efficiency. And at the beginning, we didn't realize it, but during time, we arrived to efficiency that is even 80% aperture efficiency. And the radiation efficiency is very good at TLK. This is done by using several types of elements, different characteristics for each element, but mostly by design. So the design is improved, controlling the alpha with the math. So today we can make an antenna for 40 dB gain. In that case, we have to control either the periodicity on everything, or with a bandwidth which is relatively small, but 5% is enough for many applications. 40 dB gain, 5%, very good. Or even 30% benefit with 28 gain. This is done by using a different approach. So in place of having the same periodicity of just a small varying periodicity, you vary the periodicity in a drastic way, such a way to manage the leakage just in the first part or the last part of the antenna, making an antenna which is almost a active region antenna, but based on leakage, based on leaking waves, not based on the like normal spiral antenna. So the gain is always high. So let us say if you would like to extend the original capability, you can improve a little bit your design. And normally this it can be done directly by homogenization process. So what we do is actually starting with the surface wave excitation, having a tentative impedance, and from there define the electrical equation. From there, you can make the surface current distribution variation pattern afterwards. But you can also do the reverse, because starting from the variation pattern, go back, make the surface current distribution, and from the current distribution and from the electrical integral equation, expand and finally nodes of the impedance. So what we call it is an inverse design. So we invert directly the electric field integral equation to find the impedance. So the impedance is expanded in terms of nodes, not the current. The current is assumed at the beginning. And this is done in cooperation with Prof, Dr. Charles, and other people outside our university. Actually, this can allow for a single point source to make a shape beam with almost arbitrary shaping. Just using just a point source, you excite surface, and you can get the pattern you wish. And this is very useful for contour spot from geosatellite. So this is the main application of it. This is one of the examples that we use sometimes goes. So it's an easy flux and a shape and a pattern that serves to illuminate the Earth from the low starlight with same every power over the Earth, but just with narrowing next this rotate in order to create the contour. When you go from the long path from the second generation to the third generation, you can also have some intermediate step, which what they call 2.5 generation, which means a multi-port duplexing. So you put more points over the surface and making an antenna which multi-port and multi-beam, in which the beamforming network is automatically done by the antenna. And the sort of example I'm going to present there before, just to show this picture in which the exhibits the difference between a 4-wavelength and a 40-wavelength antenna. So a 4-wavelength antenna, 40-wavelength is down with like the same technology. It's just smaller, so you can also scale it. And the same technology allows you to make a twin beam that ranges from 20 dB gain to 30 to 40 dB and more gain. This allows to make a very simple thing, so to cover an hemisphere with several beams that are a little bit larger, using a curved conformal structure. So you put some of these small patches. It is clear that you don't cover much very well the entire surface, but eventually you can cover the beams. This is an example that is done in cooperation with the wave up and multimetas, which is a 46 beam of 30 gigahertz for avionic application. That's it. You with a simple switch, but this is another for naval application, which you have a worker bound beam, and you see that inside there's a very simple switching network that feed the various point. This is for dual pole and receiving and transmitting antenna, and you can have a very simple structure, very low cost, actually. Now, going toward a single aperture with a roof beam on top, actually, there is a very simple concept to design this antenna. Suppose that you have an antenna layout in which the beam is broadside, and you superimpose an impedance with an elliptical beam that goes in the other direction or in the other direction again. So you superimpose in some way some trees the mathematical expression of the impedance, and you realize the summation of it. You realize it with a simple element, and you fit it in 3 points, and each one of the surface wave inside by 1 point interact with the individual of holography and get 3 different beams in this case, for instance. This can be done as an example in which you can cover with overlapping, partially overlapping the impedance several beams, and this actually is useful in order to cover better your surface if you would like to cover an hemisphere without scan losses. So this allows to increase the number of point source, decreasing the thickness of the beam width, and cover it with much more productivity the entire hemisphere. So you can also do it by complete overlapping of the impedance in place of partial overlapping. So you have 3 overlapping like that, which cover an entire square, and with the 3 points you get 3 different beams. In that case, it's better to minimize the interaction to go and scan in the other direction, and this is a better three-dimensional view. This is something that we have done with the UTS, University Technology of Sydney. There are 7 point source into global superposition of holography that gets 7 beams with 7 point source. So it's like that the surface can get directly the beam forming and make a different beam. But this is something that very simple to be realized. The problem is the interaction between point source and the improper holography that creates some noise or cycles. But eventually, this is anyway something that you can do, and what we are doing is trying to minimize the level of cycles by using non-radiating waves over the surface. You can use the same trick even for obtaining dual frequencies. So you excite one point with one frequency, the other point, the other frequency, the two holography are different periodicity. When you overlap together, you get something like the map here. And this is something that Gonzalez constructed when, and the results are quite good for 25-30 years. This is useful, especially if you take advanced analysis antenna. You need a very separate frequency in the 2 directions. The other thing is how to control the polarization with the plexing. So we have 3 ways to do it. One is again overlapping polarization. The second one is exciting 2 modes over the surface. And the other is exciting an inward and outward wave over the same surface. I will concentrate a bit on this third method for lack of time. And this is the arrangement that is the problem that is you can excite the 2 waves with the 3-axial cable. So the external part of the 3-axial excites a power plate to a backbone that through a corner goes on the top. So you excite from that to the periphery, and you can control the right-hand signal polarization from that when you excite it from the center, and you make the other polarization. So the left-handed and right-handed polarization from the 2 modes, the 2 ports. This is what happened actually. You excited the internal port and the surface wave of excite there and go back. In this case, we don't have any empty metasurface on top, just an electric slab. So we use this trick actually for measure the efficiency of the feed for launching the surface wave. And if you make the S12 actually this is something that is almost absorbed by the second port, by the external port, it absorb everything from second port. If you excite the port 2, indeed you make on the paddle plate and you absorb from port 1. Everything is reciprocal. If you add the surface plate on top, so metasurface on top, actually the S12 drop down drastically because of the radiation. And I said, depending on which port you excite, you get a right-handed or left-handed circular polarization. If you this data tail, it's quite difficult to make the excitation with that. We have a Quasar strip that gets for the external part of the Quasar cable, and now we are constructing measuring the entire antenna, and soon we will have. These are numerical results actually, which your efficiency is 60% for multi-way. And there is a very difficulty in doing that because the amplitude of the alpha that we make the generation of the point vector on top is not unidirectional. So you have to, the optimal in this way is not the optimal in the other way. So you have to compromise the two in making an aperture that maximizes the efficiency. And Ravikant is one of the applications to do that with a nice work in doing that. If you compare the three methods, actually this is the one that gets larger benefit. Now, the other way around for making the path from 2G to 3G is the multiport duplexing by together with multiport is the mechanical rotation. Sorry, the mechanical rotation is something that is able to cover with continuity the beaming with respect to the electronic one. So sometimes it's useful. And if you look at this picture, here is again the surface wave, but now the surface wave you run over the metasurface, which the gradient is in one direction only. So we have a modulation like that, and there is a tilted wave that with respect to the gradient of the AES that form a certain angle, and you can project the k vector of the surface wave into the direction of the gradient in the orthogonal direction. So in the direction of the gradient, your wave of field the periodicity in the other direction is not field the periodicity, so it remains constant. In the other case, it's affected by the multiplicity of the Fourier waves. And this means that your beam is going into a tilted direction with respect to the normal of the surface. And what happened indeed is that you can cover changing the angle and entire path inside the visible region, which is a locus in blue in their picture. So actually, depending on the direction of the wave of the gradient, you can scan the beam in one line over a plane. And if you rotate totally the antenna, you can actually cover the entire space with the beam and with continuity. So this is something nice. The problem is how to generate the surface wave over the planar surface wave. You can do it with a rubber lens. The rubber lens draws this gradient at the surface and create the beam. But this is not good for radio frequency because you need a very large aperture and the efficiency of the aperture will be very low. So in this case, it would be good to have a rubber lens to do it, but eventually the rubber lens will be done on the bottom and using the parallel plate will run at the corner in order to get the line away from over the top. But if you use this rule that has been shown by Oscar before, you cannot do it. The simple reason is that the wave that encountered the corner is reflected following the square law, and this does not allow the ray to be parallel on top. So eventually, the right waves that do the right job is the one that goes into a turning point and go back in such a way that after the corner they reflect all parallel with respect to the axis. And what happens actually here, that there can be make this equivalent refractive index that do the job and exactly derived the same way as the original Gutenberg paper. If you look at the Gutenberg paper, how it derived this relation, it's quite difficult to understand. So we need some time to understand how it did it, and afterwards we extended it into this very simple. Actually, when you go in this way, you discover, or you naturally discover that there is a caustic point close to the middle pan between the center and the periphery. And so, in place of putting the source on the periphery, you can put the source in the middle in such a way to save space. Actually, this allows you to make the background directly without having any obstacle on the other side. And this allows to use two possibilities that are investigated by David Gonzalez recently. One is several point source or several horns inside, or a single horn that rotates. And this is obviously more useful for electronic scanning, and these actually get the benefit of a continuous scanning of the beam. Actually, here the Metasurface is done by pins with staircase. We can do other technology. This is one of the first alternatives we did with Jose Garcia, David, and others. The same technology for the gradient Metasurface on top and the Gutenberg lens on the bottom. Actually, you can, with scanning, there is sort of dependency of frequency. This can be overcome by using a trick that was introduced by Oscar some time ago, so making a glide symmetry on top and bottom of the lens in such a way to enlarge the bandwidth. Now, in this case, we can cover bandwidth from 25 to 35 meters with almost no problem in feeding. So eventually, in order to get the other scanning, this is one other example in which you put just one stab on top of the Metasurface in such a way to create a certain directivity. Is not much because there is a single slot, and eventually however, this was done for checking the technology. You can scan from 27 to 39 gigahertz with a gain about 32 dB, and even more, if I remember well, yes, it's 25 dB. But now what David and Christos did was more stabs in series over the top of the surface in such a way to make the beaming everywhere with a good directivity. So eventually, this is the final layout with the bar stub. The stub are different in width in such a way to create the right alpha that allows the good compromise with respect to several beams. These are the recent measurement that David did in Venn. The Christos Giridos is the one that was working on it for his PhD, and he will discuss the PhD in a couple of days. Now, there is another way to create a deep scanning. This can be done with the same concept, but in place of having a surface wave, you have a plane wave. The plane wave that drives a certain direction from the Metasurface. What you do here is something that allows to go into the visible region, and if you are able to suppress the zero with that filter out directly from the Metasurface. So eventually, when you actually rotate the filtered antenna, you can scan everywhere as before. you can produce the beam that serves for the net deflector by using a surface-based surface antenna. And this is problem of the final layout is something like that. So you put on the surface, you rotate. So rotating antenna and rotating the surface between the two freedoms to make this can be everywhere in space. However, this is software of the impairment of the needing the rotary joint. So it's better probably, and what we are following this path, having just a non-rotating the surface of the on top of it, having two linear gradient, unigradient, let's say, double layer that get the dual beam. Eventually, this is the final layout. So these are the part of the final radiator designed by AES, so all going one. And on top of it, you have two top cover. So they are on that screens, each one composed by 3 layers. In each of these 3 layers, you have elements that rotate in space. And when you go inside to the right hand of the circular polarization, you exit with a tilted beam in the left-handed circular polarization. Again, the second top layer, yet again to the right-hand circular polarization. You can demonstrate that in this screen, you can do it. It's conceptually very interesting, but the problem there is actually to filter in a good way the direct beam. So actually they are either on the front ways. So most of the time, the design of this antenna is done in order to suppress the front walls. Actually, if you do it, the linear polarization doesn't work. It works very well in circular polarization. So this is another technology. Actually, you can rotate and put the beam everywhere. If you wish, this the design was done like physical dimensional power and remap. So eventually, these are the rotation of the 2 screens and correspondingly the direction of the beam. These are what was the prototype of the 50 centimeter 39 gain metasurface antenna on the bottom. And eventually, we fabricated the prototype and we get some nice measurement. However, the problem there was about the. Let me check if I can actually. I know. There was a way to move that. So these are actually the antenna in operation. There is a transmitting antenna, receiving antenna, and each one of them has a tool for mechanical rotation for the 2 screens that allows to make blocking the sunlight or the sunlight and making it to the blocking. This allows also with a certain difficulty to manage and offer from one side to the other. This of the another is still a problem, but I mean, this was something first prototype that way back was done. So this was the measurement. So let me point out the scanning fourth gain antenna is not easy at all. So even if you make a phase array, you can do it. However, phase array costs a lot. So if you make a number of technology for the gain, there are several technologies that allow to reduce the cost. The gamma rays has shown a lot of them. However, adding a 40B is quite difficult. So I have probably 5 minutes more. Okay. So let me go into now the full control of the surface by using the electronic control. So there are 2 ways to do it. I mean, several ways, but this one is more close to what I presented before. So if you look at the formula that relate the beam or the impedance, you see there are 2 parameters. One is the periodicity, and the other one is the average impedance. So you can actually change or the impedance or the periodicity. Now, changing the energy impedance allows you for only one control. And this actually is powerful because with only one control can actually change the physiology, change the development, and changing the development can be. If you eventually try to compare these two techniques in the KA band, due to the limitation of the actor in the KA band, you can have a reduced scanning if you have one single control. So these are actually multiple controls. Where multiple controls can scan like 30 degrees, 40 degrees almost. When you are in per second control, you can scan minus 25 minus 30 degrees. And that is the price that you have to pay for KA band for not having the good actors. Now people are doing it much better, especially K-Data is doing constructing actors that are much better than these, so they can also use it to be cooperating with them. The other way around is the second way is changing the peak dials. So that I'm using my actor peak dial. The pin dials, you actually inject the guided bolts or the surface wave into the surface, and you have some of dials that are off, some that are on, and changing the periodicity of the dials, you can actually produce the pinning. Actually, this is some example done by wave up in the KA band again. And you see that if you make one dial on and two dial off, you can scan it good, let's say, stability of the beam into a certain radio frequency. When you take one on and three off, you get another beam. And if you want to cover the space in between the two beams, actually you can make it 2.5 periodicity. So you make one out, three up, one out, one out, three up, one out, three. So you can statistically cover a better than with continuity some other states. You can use this by using the digital control and shifter on one side, or you can do it even in 3 dimensions. So actually, the issue here is to decide, which is the combination of elements that are on and off in such a way to cover all the states. And this was done recently, and this is the results that we got. So having each one of these in the UV plane is the contour beam at 3 dB that are all together in such a way to cover from 34 to 37 years all the possible states in the UV plane. And in order to do it, we were obliged to get an input source that excites the surface. So one direction, the other direction. So that part of the antenna will be in the form of the other one backward. So I believe that I'm almost finished. So it's under realization, and it works very well. This is another way around to scan the beam. Let me just show this last picture that we got recently some interesting results about how to inject the optical information directly into the antenna. So we printed the antenna on silicon, and we shine on the antenna a laser beam with light, which actually change the sigma of the antenna. When we do it, actually do reduce the efficiency of the surface wave launching. It means that the gain of the antenna drop drastically, even 10 dB, with not much power. So with a few power density, actually you can get a complete mismatching, and this means that you can make an on-off modulation of the beam directly in optics. This is the first attempt at the field. We are every other way to illuminate obviously, but this was just something interesting. So in conclusion, from the 2G antenna to the 2.5G of mechanical rotation of flexing, we are arriving gradually to the tunable, full tunable Metasurface. So for that, I will finish my presentation. Thank you much for the attention.